Hello friends. So today we are going to discuss 5 questions, and in this first question it states that a spinning wheel, mass m, moment of inertia I naught, sits at one end of an axle of length a. The other end of the axle is hung from a string of length b. The wheel spins with angular speed omega s. The whole axle plus wheel precesses uniformly around the vertical with the angular speed omega. The string makes a small angle beta from the vertical. So we have to find out this small angle beta with respect to the vertical, that is asked in this particular question. And for that we can just draw the figure. We can draw just approximate figure. So let us suppose we are having, suppose this is our top ceiling and this is the vertical, and we are having a string which is at an angle of beta to the vertical, and to the other end of this string we have connected an axle, and that axle is, we can just make it like a square, much more easier to understand. And we are given that the length of the axle is our a. So this length is given as a and the length of the string is given as b. So this length is given as b, and let us assume that the distance between the vertical and the wheel is our x, and the various, there will be two forces majorly. One will be mg, that will be at our axle acting downward direction, and other one will be our tension T. Therefore we can divide this tension into two components, and so this angle will be also beta. So we are going to get this as T cos of beta, and this will go T sine of beta, not theta. Okay. And so we can write the linear equation of the motion, and we know that first equation of the motion will be our with respect to the vertical component, that will be our combination of T cos of beta and our mg, and other one will be our the horizontal component, that is our T sine of beta. Okay. And this system goes around, okay, we are given that it is moving with the angular speed of omega. Therefore we can write the linear equation of the motions. The equation of motion, and first equation of motion is our along y-axis. So we have x-axis and our y-axis, and for y-axis we can write that our T cos of beta minus mg will be equal to 0. And second is our t sine of beta, and that t sine of beta will be our equal to, we can say that our t sine of beta, we can write this as our in terms of our angular m, and we have this as our omega square multiplied by our x, okay, because it is going to rotate in a circle. It will be doing something like this in the circle whose radius is our x. Therefore, we can write our torque that is our tau will be equal to our is our A multiplied by our mg. Okay, so this comes as our A times mg, and we also know that the torque is nothing but our derivative of our the angular momentum ls and our t. Okay. And if we so from here we can write that this will be equal to our omega times our ls, and that is equal to our ls is our I naught multiplied by omega s. Okay, so we can write this will be equal to our omega times I naught and omega s. And we are given that this beta is very, very small. Therefore, we can use the approximation that our cos of beta will be equal to 1 and sine of beta will be equal to beta. Okay. Therefore, we can say that our we can write that our cos of beta is approximately equal to 1, and we can also write that our sine of beta is approximately equal to beta. Okay. And sine of beta, from, let us call this as equation number 1 and this as our equation number 2. Therefore, from equation 2, we get this as t sine of beta is our beta is equal to m omega square times x, and from here we get that our, and using, let us use both the equations, and that is going to help us because, okay, let me write here from beta is equal to our m omega square x divided by t, and if we use our equation 1, cos of beta will be equal to 1, and we can say that our t is equal to nothing but our mg. So you can say from equation 1 we can write that the t times 1 is equal to our mg, because cos of beta is our 1. Therefore, we get that our beta, which is our m omega square x, and we substitute value of t, which is our mg. And here this m and m cancels out. Okay. So we get that our beta is equal to omega square x upon g, and we can substitute value of our omega, and we get that our this will be x by g, substituting value of omega, which is our mgl upon 1 second. Sorry, there is no L. Yeah, that's why. This is our MGA. We have this as MGA divided by this and this. We get this as our I naught divided by omega s and whole square. And we also know that this total length x will be equal to a, and we can just use triangle law and we can find out that our x will be equal to a plus L sine of theta. Oh, sorry, not L, but that is our b sine of theta. We know that our x is equal to our a plus b sine of beta. Okay. And sine of beta is our beta. Therefore, we can say this is equal to a plus beta times b. So we substitute value of beta and we get, or we can substitute value of our x in this equation. Therefore, we can write that our beta is equal to 1 upon g, and this comes as mga upon I naught omega s whole square times a plus beta multiplied by b. And we can just solve this, and we need beta on the other side. Therefore, let us assume that this entire term is equal to some constant. Okay. Because this will be, so let us assume that this is equal to another constant, that is our c. So we get our beta will be equal to our c times a plus beta times bc. So we get this as, we can combine these two terms. Beta is equal to 1 minus bc is equal to a times c. Thus we get that our beta is equal to a times c divided by 1 minus b times c. And we can further write it as a upon, and or we can keep it like this, doesn't matter. Okay. So this is our final angle beta. And next question. It states that a milestone is modeled as a uniform solid disk of mass m, radius b and width w. It rolls without slipping in a horizontal circle of radius r with a constant angular velocity omega. Determine the ratio of the normal contact force exerted by the surface on the milestone to the weight of the stone. So we can once again draw an approximate figure for that, and we are given that, let us suppose this is a a support system, and to this support system we have connected this milestone which is as a solid disk. So we can say that this is our solid disk, and it is going to move in a circle of radius r. So obviously this will be equal to our r, and we are going to have two forces that will be acting. One will be our mg in the downward direction, and other one will be our normal that will be acting in upward direction. So these are two forces, and we are supposed to find out their ratio. And it is rotating about this circle in an angular of omega. And this radius of this, because this is basically a wheel, so if we look from side it will be looking something like this. So if this is the center, so its radius is given as a b. And so we are given that this wheel is, rather we can say solid disk is rotating without slipping. So we can say pure rolling, no slipping. So you can say we are having pure rolling, no slipping. So therefore we can say that its angular velocity about its own axle, if that is omega, so we can write that it's spin angular, okay, because it is going to, you can say, roll here also, and that is our omega. So there will be two motions, one will be rotation about its axis and other will be revolving around this particular support. So we can say its spin angular velocity about its own axle and let us suppose that is of omega, and that will be equal to over omega r divided by b. And we can also find out the moment of inertia about its own central axis. You can say moment of inertia of, it is called as a solid disk, moment of inertia of solid disk about its central axis let us, we call this as our I, and this I will be equal to 1/2 m and radius square. Therefore we can write that the spin angular momentum and let us suppose that spin angular momentum is our L, then this L will be equal to I times omega, okay. And we already know our I as well as our omega, and if we substitute them we get that our I so we simply substitute it, and value of I and omega, we get the spin angular momentum, that is of L, will be equal to half mb square times omega, and omega is our omega r upon b, and here our b and b, this cancel out the square, so this will be coming as our half m b omega r. And we can also say that from here we can find out the magnitude of the torque. Therefore we can say that the torque that's our tau will be equal to omega times L, and this gives us our half mb omega square times r. Okay. Or we can also say that this torque will be also provided by the net vertical force. So we are going to have torque, same torque provided by two different you can say things. First one will be this horizontal angular momentum. It is going to provide a torque about the vertical axis, and another torque will be provided by the net vertical force. So we can say that this torque is provided by the net vertical force, and this net vertical force at the wheel's radial position. At the wheel's radial position. So we know that the distance between it is given as r, and we have two forces, mg in the downward direction and normal in the upward direction. So the net force we can write is our n minus mg. So we get this is equal to n minus our mg. This is net force multiplied by the distance r, and this will be equal to the torque which we just calculated, that is our half mb omega square times r. And here this r and r cancels out, so we get that our n minus mg will be equal to half mb omega square. Okay. And from here we can also write that n will be equal to mg plus 1/2 mb omega square, and we are supposed to find out the ratio. That the ratio we are required is n upon mg, so we are going to divide this entire equation by mg. So here this mg and mg, and here this m cancels out, so we get n upon mg will be equal to 1 plus, and this comes as b omega square divided by g. So this is the required ratio. Okay, that was asked for. And one second. Okay, so next question. It states that a coin of radius b, mass m, rolls on a horizontal surface with a linear speed v. When the plane of the coin is vertical, it rolls in a straight line. If the plane of the coin is tilted at an angle of alpha, the coin rolls in a circular path of radius r. Determine the expression for the tilt angle alpha in terms of the given quantities. You may neglect the small difference between r and the actual radius of path traced by the coin's center of mass. So in this case, we are given two situations. In the first case, it states that the coin is moving in the straight line, and then it is tilted, the plane of the coil is tilted by angle of alpha, and as soon as it is tilted with angle of alpha, its tendency is to move in a circular path whose radius is given to us as r. And so we are mainly interested in the second part, that is as soon as we are going to tilt the angle of this plane angle of our coin. And for that, obviously there will be a central axis about which it is going to go around, and let us suppose it is moving with the angular speed of over omega around this central axis, and it is going to follow a circular path something like this along this axis. And we can just draw an approximate figure for this coin, and let us suppose this is our horizontal and its plane is tilted. So we are going to make a, so this is our coin and it is tilted by an angle of alpha. So the axis of the coin will be something like this, so it comes as alpha. And here let me draw this separately. So we are having a coin, and this is our axis, and it is the axis means the horizontal line when it is straight, and there will be the tilt axis of this coin, and this is our angle of alpha. And here we are going to have two major forces. One will be our mg acting in the downward direction, and other one will be our normal that will be acting in upward direction. Okay, so these are the two major forces. As of now, if required, we can add later on also. And this, suppose, is our radius r. And so first of all, here we are going to find out the moment of inertia about its center, and then we are going to find out the moment of inertia about its edge, means one of the contact points, something here, okay, by using our parallel axis theorem. One second. Yeah. So let us make that moment of inertia of the coin about its center. About its center, and let us call this as IC, which will be equal to over half, and its radius is given to us as b, so this will be half mb square. Okay. And moment of inertia, let us suppose we call this as point as P, contact point. Therefore we can say that moment of inertia about point P, and let us call this as IP, so we get this as our IC plus our its mass, and we have this as mb square. Okay. And we get this as our IP will be equal to half mb square plus mb square, giving us 3/2 mb square. So this is our moment of inertia about point P. And we can also find out our angular momentum about this axis. Therefore we can say that if it is rotating with the angular speed about its axis is, suppose it is rotating with our omega, therefore we can say that the angular momentum that is L will be equal to I P multiplied by omega, and this comes as our 3/2 mb square times omega. And this our angular momentum we can okay, and let's find out value of the torque. We can come this to angular momentum later on also, and this angular momentum we can divide it into you can say that this will be our angular momentum L, and therefore we can write that our okay, so if we are having this is our angular momentum, therefore it's 2, we can write this as our L sine of theta. Okay, so we are going to get this as our L sine of theta, and other one will be our L cos of theta. Now we come to our the torque, and you can say that the torque is given by, which is our tau, and our radius is our b, and we are going to have force because of our gravity, that is our Fg. Okay, and this Fg we can just divide it into two components, and we have our mg. Okay, so this is our Fg, which is nothing but our mg, and we are given that this angle is our alpha, and so if this angle is of alpha, we can say that one second. Yeah, so if this angle is alpha, so we are going to have this will be our 90 minus alpha. One second. So we are having mg in the downward direction, and this angle is our alpha. So we are going to get this angle will be also our alpha, and we get two components. One will be our mg cos of alpha, and other one will be our mg sin of alpha, and this distance is our b. Okay, therefore our Fg will be equal to our mg sin of alpha. Okay. So we get that our torque will be equal to, in terms of magnitude, we can say our b and our mg sin of alpha. So this is our value of the torque, and torque we can also find out by the derivative of our angular momentum. So we can say our torque is equal to dl upon dt, and our L is our, we are going to get this as our omega, and we have this as L sin of alpha, and this will be equal to same. So we get this as our b mg and sin of alpha, sorry, cos, my mistake. cos of alpha. Okay, and we can substitute our value of our omega, and that is almost done now. Okay, because this will be giving us, we can write this as our tangent of alpha will be equal to, we have our omega L divided by B times mg, and we can substitute value of our L is our 3 by 2 mb square omega. So we get this as our omega upon b times mg, and our L is 3 by 2 b square omega, 3 by 2 b square mb square times omega. And here this b goes by square, m cancel out with m, so we are left with our that tangent of alpha will be equal to 3 by 2 b times omega and multiply by omega. And we can, I think, yeah, this is done. And if required, we can also find out the radius value. We know that our linear speed v is equal to omega times our r. So from here we can say that our omega is equal to v upon r. Therefore, we can write our tangent of alpha is equal to 3 by 2 bv r times omega. Okay. And sorry, we can write that our v is equal to omega times b, not r, and this will be equal to omega times capital R. Therefore, we can say that our radius r will be equal to 3v square divided by 2g tangent of alpha. So from here we can also get the radius part. I think, if I'm not wrong, one second, LBMG omega omega. Yeah, I think this looks okay. So next question. It states that a uniform stick of mass m and length L rotates with a constant angular speed omega about a fixed axis in zero gravity. The stick makes an angle theta with the axis of rotation and is held in place by two strings, each attached perpendicular to the axis. Determine the tension in each string. Okay. So we can divide this question into two parts. This particular we are going to solve with zero gravity, And in the second part we are going to consider the gravity part also. And we are given that is a stick. So let us suppose this is a stick, and this is our vertical part. It is rotating around this with our omega, and there are two strings that are attached, something like this. Okay. And we are given that its mass is m and length is l. Okay. And it is making an angle of theta with this axis. So first case, we are going to find out, without gravity, we have to find out the tension in the each string. So the strings are same, so the tension in the string will be same. So we are going to find out one and just sort out for the other part also. And in this case, we can say, or rather first of all, we can divide our this angular speed into two components. One will be our, we can say, the parallel component. This is angle theta, so we can call this component as our omega parallel, and the other component we can call this as a omega perpendicular. Okay, later on we can substitute its value. And this is the center of mass. So we can say that our moment of inertia of this stick about its own center. Moment of inertia of stick about its own center. Okay. And let us call this as our I, which will be equal to over 1 by 12 ml square. And like we have drawn here two components of our omega. So this parallel component of omega is in the same direction, or we can say is parallel to the stick. Okay, our stick is also in parallel part. So only this parallel component of omega is going to contribute to this rotation. So we can say that only perpendicular component of angular velocity which is our omega perpendicular, and we can write this as a omega sine of theta, contributes to this rotation. Therefore, we can find out its angular momentum. So we can say our angular momentum, that is, L will be equal to moment of inertia and omega perpendicular. So we get this as 1 by 12 ml square, and we have omega sine of theta. Okay. And we can also find out we can find out torque by the type variant of our L. Therefore, we can say that the applied torque is nothing but our rate of change of horizontal component of L. rate of change of horizontal component of our angular momentum. So we can say torque is equal to dl upon dt, and that will be equal to over omega L cos of our theta. And now we come to the tension part. So there will be a torque due to the tension, and that is because that is at the opposite end of this. So we have to remember that our torque due to string tension and there are two strings each having tension T. Therefore we can say that torque due to string tension T about the center of the stick, about center of the stick. So which basically means that this is our stick and this is our vertical portion, and our string are connected like this, and this is angle theta. So there is a tension T, and we can find out this vertical perpendicular distance in this particular case, and this length is our L by 2. So we get this perpendicular distance will be equal to L by 2 cos of theta. So we get that our torque tau will be equal to, and same to the other side also. So this will be twice T, and the perpendicular distance is our L by 2 cos of theta, and T cancels out. So we get that the torque will be equal to TL cos of theta. Now we are having two equations of the torque, omega L cos of theta and TL cos of theta. So we can just equate them. Equating torque, we get TL cos of theta will be equal to omega L cos of theta. Cos of theta. And we can just cancel out cos of theta, and we substitute value of our L. So we get this as our TL, and omega L is our 1 by 12, and angular momentum 1 by 12 ml square omega sine of theta. Ml square omega sine of theta. And this length goes by the square, so we get our tension T is equal to 1 by 12 ml omega sine of theta. Now in this case we only considered the torque because of tension T, because it is in question, it is given that G is 0. But in the second part we are going to consider G also. So therefore at the center of mass there will be a mg is always acting in the downward direction, that is going to additionally produce a torque. Okay. So if G is 0, this torque we have not taken into the consideration. Okay. Rest of the things are going to remain same. And so we can consider the second part, in which we can say that G is not equal to 0. Okay. And we just calculated that the torque total due to the strings is equal to, this is ever twice T L upon 2 cos of theta, and we can simply write this as TL cos of theta. And we can also find out this torque due to rotation, and for that we can say that, but we calculated that also. Okay, we calculated that, and here we can just substitute value of our L, and okay, we can use same. So we can say our torque due to rotation and let us call this as tau rotation, which is our dl upon dt, and which became as omega L cos of theta. Now here we substitute value of our omega, sorry, omega not but L. So we get this as our tau rotation will be equal to omega, and we have this as 1 upon 12 ml square omega sine of theta multiplied by cos of theta. So we get this as 1 by 12 ml square omega square sine of theta and cos of theta. Now there will be an additional torque that will be because of the gravity. Rest of the things we just picked up from the above part. So we can say our torque due to gravity. Okay. And so we are going to have this mg acting in the downward direction, and this is our distance is our L by 2, and we can write this as distance of center of mass is our L by 2. Therefore torque due to this gravity will be equal to mg L by 2 sine of theta. Okay. Because this angle is our theta here also as well as here also. So we can divide this mg into two components. This will be coming as mg cos of theta, and other one will be coming as mg sine of theta. And the torque will be produced by only the perpendicular component, which is our mg cos sine of theta. And this mg cos of theta is parallel along the stick. Therefore we can say torque due to gravity. We can write this as our tau gravity will be equal to our perpendicular distance, and this will be equal to L by 2 mg sine of theta. Sine of theta. Okay. And we have torque due to gravity, and we also have the torque due to our string, and we have torque due to rotation. So this entire system is in equilibrium. So we can say total torque balance for our equilibrium. We can write that our torque due to our, what we call this as tau total string, will be equal to torque due to rotation plus torque due to gravity. Okay. Now we simply substitute their respective expressions. So we get this as TL cos of theta is equal to 1 by 12 ml square omega square sine of theta cos of theta plus 1 by 2 mgl sine of theta. And here this length cancels out throughout, and we can simply solve it for our tension because that is our required. So we can say tension T will be equal to 1 by 12. This comes over ml omega square sine of theta cos of theta divided by cos of theta plus 1 by 2, and one second, this is forgot one thing, that is our G is missing. So we get this our mg sine of theta divided by cos of theta. So here this cos theta cancels out, therefore we get that our tension T is equal to 1 by 12 ml omega square sine of theta plus half mg tangent of theta. Okay. So this is our, and if we put G as 0 here, so this term is going to vanish, so answer will be coming as same. Okay. So we come to the next question, and this next question is our okay. It states that a uniform rod, thin rod, is placed with one end resting on the edge of a table in a nearly vertical position, then released from rest. Determine the angle of rod makes with the vertical at the instant it loses contact with the table. Consider following two limiting cases. First case, the edge of the table is smooth, negligible friction, but has small single step groove that prevents the rod from sliding sideways. And part B, the edge of the table is rough, high friction and very sharp, so that the radius of curvature of the edge is much smaller than the flat end face of the rod. Half of the rod's end face extends beyond the table edge, so that when released the rod pivots about the edge. both the cases it is about the pivoting of our vertical rod, but with the different conditions. Okay, the statement looks a little bit typical, but basically it is talking about, in the first case there is negligible friction, and the second case there is friction. Okay, that's the only difference between the two. The rest of the things doesn't matter at all. Okay, they are just your statements, and the situation is going to change only because of the negligible friction as well as the value of the friction. Okay, that's only the difference. So we can just draw an approximate figure, and we are given this table. Suppose this is the edge of the table, and initially we have a rod. Suppose this is a rod, and total length is given as, it's not given, okay, let's assume that it is our L. Length of the rod is our L. So if this is our center of mass, so its length will be equal to our L by 2. Okay. And as it is going to pivot, so it is going to form something like this. This is the upper edge. Similarly, the center of mass also going to form something like this. And let us assume that at any particular instant, this rod is at this position, which is making an angle of theta with the vertical. And we can, so now our center of mass, let us suppose this rod is our A, and B, center of mass is given as C, and new center of mass position, because everything will be about the center of mass, so let us call this as our C prime. So we can find out by how much distance rather, this center of mass is going to fall, and let us call this as our delta of H, because we are going to use the energy part. For that we are required this particular thing. And so we can just complete this figure. Suppose this is our extended portion. So theta, this we can find out. Okay, let me draw it here. So this is our point B, and this is our C prime. So we are going to have this length, we will have L by 2, and with the vertical it is angle of theta. So with the horizontal it is going to have our 90 minus theta. Okay. And we are interested in finding out this particular height. And our initial, this C, let us call this is our position of C, and if we extend this, we call this as our delta of H. Total length we know is our total number, center of mass length is our L by 2, so this length will be our L by 2, and this is 90 minus theta, so we can say this will be coming as L by 2 and cos of theta. Okay, ideally it will be sine of 90 minus theta, which will be giving us cos of theta. Therefore we can write this delta H will be equal to L by 2 minus L by 2 cos of theta. Okay, so we got our this length part. Okay, so we can say that the center of mass falls by delta H, which is equal to L by 2 minus L by 2 cos of theta, and simply we can write this as L by 2 1 minus cos of theta. Okay, and we know that its mass is our m. So in the downward direction, we are going to have this as our mg. Okay. So we can also find out the potential energy lost. So we can say the potential energy lost by center of mass, and that is equal to over mg times delta h, and that will be giving us mgl by 2 1 minus cos of theta, because we are going to use the conservation energy, that is potential energy lost by the center of mass is equal to kinetic energy of rotation about the pivot point, and pivot point is our B. Okay. So we know that our moment of inertia about the pivot point, which is our B, you can say that moment of inertia about pivot, and pivot is at the end of the rod, so that will be equal to over I is equal to 1 by 3 ml square. So from here we can say our rotational kinetic energy is equal to over half I omega square. Okay, and it is with the angular velocity omega. So we substitute it, we get this as half I is our 1 by 3 ml square, and we have this as omega square. So this will be coming as 1 by 6, and we have our ml square omega square. Okay, and now our energy conservation, you can say our energy conservation, we can write this rotational kinetic energy, let us call this as E rot. So we can say that our rotational kinetic energy will be equal to this lost potential energy, that is, let us suppose our delta PE, and let us call this as our KE. So we can say KE rotational will be equal to lost potential energy. So we get this as 1 by 6 ml omega square, 1 by 6 ml omega square is equal to potential energy lost is our mgl upon 2 1 minus cos of theta, and here ml square. So here this square cancels by L, and 6 goes by 3. Therefore we can say that our omega square is equal to, this will be coming as 3 mg by L, here m and m also cancel out, so we get this as our 3g upon L 1 minus cos of theta. This is the angular speed at a particular angle, that is our theta. Now there will be accelerations that will be also associated with the center of mass, okay, and we are mainly interested in the centripetal acceleration. So we can say that our centripetal acceleration of center of mass, and let us we call this as our AC, and AC will be equal to omega square and the distance of from the pivot, that is our L by 2. and we already know our omega square. Therefore we can say that our A of C is equal to, we have this as our L by 2 multiplied by 3G upon L 1 minus cos of theta, and here this L and L cancel out, so we get this as our 3 by 2 times G 1 minus cos of theta. So this is our acceleration of the center of mass towards the pivot, okay, or we can say towards the rod's circular path. This is our towards the pivot point, so that is our B, towards pivot point, which is our B. And we can also find out the tangential acceleration of the center of mass, so we simply derivate it with respect to time. So we can also find out tangential acceleration of center of mass. Let us call this as A of t, and A of t we know is our perpendicular distance, that is L by 2, and our first derivative of our omega, and we already know our omega, so we simply calculate its derivative. So we know about that our derivative of our omega square will be giving us 2 omega dot will be equal to, and 3G upon L will be constant, and this comes as our d upon dt of 1 minus cos of theta. So from here we get this as 2 omega dot is equal to 3G L, and this will be coming as our sine of theta and theta single dot. And from here we can say that our, okay, and this is the derivative of our angle is nothing but our omega. So this omega and omega are going to cancel out, therefore we get from here that our single derivative will be equal to 3 by 2 G upon L sine of theta. Therefore we can write that our tangential acceleration, that is A of t, will be equal to L by 2 3 by 2 G upon L sine of theta, and here this L and L cancels out, this comes as our 3 by 4 G sine of theta. And now we know both components of our this centripetal acceleration as well as the tangential acceleration. Now we are interested in finding out our force, okay, because it is said that we have to find out the particular angle at which the stick leaves the table. So we can say whenever there is a certain condition that it is about to leave, the contact force, that is our normal, comes equal to 0. So we are interested in finding out what will be our this equation. For that we can just draw the figure once again, and we are having a stick, and this stick is at an angle of theta with the vertical, and we can have our mg in the downward direction, and this only B is the point of contact, therefore the normal will be in this direction. And we can divide, we can just divide the component of this mg, and so this angle will be also about theta. So we are going to get our mg sine of theta and mg cos of theta. Okay. And the centripetal acceleration, that our A of C is in this direction. Okay. And as it is going to trace a circular path, the tangential acceleration will be somewhere in this direction. Okay, this is the approximate figure which we can draw. And we are only mainly interested in our normal equation part, and therefore we can say our this normal minus mg cos of theta is going to give us a centripetal acceleration equation. Okay, or we can say that our equation of the motion along the radial path. So we can say that along the rod, and we can write this will be equal to over n minus mg cos of theta will be equal to minus of m a times c. Okay, and we already know value of AC, so we substitute here and we get this as normal minus mg cos of theta is equal to minus of m, and centripetal acceleration is our 3/2 g1 minus cos of theta. 3/2 g1 minus cos of theta. And we can simply put n is equal to 0, or okay, let me solve to the right side, then we can put n is equal to 0. So we get this n will be equal to, we can take mg as common, and we get this as cos of theta. This will be our minus 3/2, and then it will be plus 3/2 cos of theta, and we can add, we get this over mg, and this will be 5/2 cos of theta minus 3/2, and for loss of contact, we know that our value of n is equal to 0. Therefore we get mg cannot be equal to 0. Therefore we can say that about 5/2 cos of theta minus 3/2 is equal to 0. So from here we get that our cos of theta is equal to 3/5. So we get this theta is equal to cos inverse 3/5. This is the value of theta when the friction is negligible. Okay. Now we come to the second part, when friction is present basically. So we have our part B, and this part A, we made the discussion where this one, when friction is approximately equal to 0. And in the second part we are given that friction is not at all equal to 0. So in this case, we have to remember that our normal will be dependent upon the value of our theta with the vertical. Because so we are here also interested in the normal. The rest of the things are going to remain same, except we have to remember that the rod is at this particular position, and we know that angle is our theta. So, and the normal is acting in this direction. So we can decompose this normal into two components. Let us call this as our n of x and this as our n of y. Okay. And so we can say that our normal component L, based on this figure, we can say that our n will be equal to over nxi plus nyj. And from our we can write that this nx is trying to force to move this our with the acceleration of ax. Okay, therefore we can write that from the second law for rod's center of mass in x direction, we can write the equation that our n of x will be equal to mass into a of x. And for our mg will be somewhere here in the downward direction. So the net force will be our ny minus mg, and that is going to give us similarly Newton's law for center of mass in y direction. So we can say in y direction we can write that our n of y minus mg is equal to our m of a of y, okay, where a of x as well as a of y are the accelerations of the center of mass along x as well as y axis. Okay. So let me put it here. So we can say that our a of x and a of y are acceleration of center of mass along x and y axis, and we can find out this value of x as well as y in terms of our centripetal as well as our tangential acceleration. Okay, we can just find out with respect to their two components. Okay. So we know that the basic, suppose this is our circle, so we are going to have our centripetal acceleration, that our a of c, and tangential will be something like this. So this will be our a of t, and the component we have taken is along this direction, and we know that our this angle is equal to theta. And let us make a vertical part here. So this angle will be also over theta. So we can divide our AC into two components. We get this our AC of y, and the other component we get this as our AC of our x. Similarly, we can find the tangential component, and our tangential component will be our AT of x, and the downward direction we are going to have this as AT of y. And the A of x, that is x component of our center of mass, is our in this direction, and our y component is in this direction. Therefore, we can say that our A of x is equal to, we can say A of x will be equal to AT of x minus AC of x, and AT of x we know that is our AT cos of theta, and AC of x is equal to our AC sin of theta minus AC sin of theta. And similarly, we can write that our A of y will be equal to AT of y plus our AC of y. And one second, sorry, this is downward direction because it is moving like this. Okay. Therefore, this all will be negative, this will be minus, and this will be also minus, so it is going to balance out. So we get this as our AC cos of theta plus AT sin of theta. So we got our component A of x as well as A of y in terms of our centripetal as well as centrifugal, tangential as well as centripetal. And therefore, we can write that our n of x is equal to our mass multiplied by our A of x. Therefore, we can write that our n of x is equal to mass multiplied by A of x. So we get this as our m multiplied by A of x is our AT cos of theta minus AC sin of theta. So we get this as our AT cos of theta minus AC sin of theta. And similarly, we can write our n of y will be equal to, and in the downward direction we have our mg, in the upward direction we are going to have our n of y. So we can say our n of y will be equal to our mg minus m A of y. So we get this is mg minus m, and our A of y is our A of y is AC cos of theta plus AT sin of theta. AC cos of theta plus AT sin of theta. And we already know that our A of c is equal to 3 by 2 g1 minus cos of theta, and we know that our A of t is 3 by 4 g sin of theta. So once again we are interested in only one part, that is our n of x is going to lose the first contact. So we can say that first loss of contact will be because our nx is going to equal to 0, and therefore we can write that our nx, and nx is our, okay, we can substitute it and then we can solve it. So we get this as our m, and we have our 3 by 4 g sine of theta cos of theta minus 3 by 2 g 1 minus cos of theta times sine of theta. Okay, and we open this, we can take our gm, and sine of theta is common, so we can write this as our mg sine of theta will be equal to 3 by 4 cos of theta minus 3 by 2 plus 3 by 2 cos of theta, and we can solve these two parts. 4 will be LCM. We can also take 3 as common. One second. This will be coming as 3 by 2 and by 4. Okay, so let me take, I'm sure this is 3 by 4 and 3 by 2, 3 by 2 and 3 by 4, yeah. So we can take 3 as common, so this will be our 3 mg sine of theta, and we get this as 1 by 4 plus 1 by 2, and 1 by 4 plus 1 by 2 cos of theta minus 3 by 2. Anyways, there is no need to solve this part. So we can, because we are going to equate nx is equal to 0, so if this term is equal to 0, so obviously 3 mg cannot be equal to 0, so either sine of theta is 0 or this second term is 0. If sine of theta is equal to 0, so we can say that our theta is equal to 0. So it means that is vertical, so which is not possible. Therefore, we can say that cos of theta, one second, yeah, so this comes as our 4 and 1 plus 2 cos of theta is equal to 3 by 2. I hope this is, so this comes as 3, so we have 3 by 4 cos of theta is equal to 3 by 2, 3 and 3 cancels out, this goes by 2, therefore we get theta is equal to cos inverse of 2. So this is our value of our theta, the second part. Okay, so this completes all the questions for the today, and thank you for watching. See you next time. Thank you. One second.